Hi everyone, sorry for the very delayed video for y'all because I was a little bit busy with recording other video as well. Okay, so apologize to my student who has been waiting for this vector video. So today will be the first video for physics formula, and in today's video we're going to talk about the very difficult topic once again. Almost every topic that I'm going through is difficult, and this definitely, if you agree with me, is a difficult topic. So in today's topic that we're going to talk about will be on vectors. So this will be a two-part video. In the first video, we're going to talk about some of the very common things that you need to know in this topic. So to lay down the basic foundation for you. So in the second video, we will just focus on dealing with how to do some of the questions that you have been struggling with. Okay, so let's get started. So vectors, there's a total of three types of vectors that you need to know. The first one is called position vector. So position vector is to talk about a point in space where you are going to be measured from the origin. So in vectors in JC vectors will be 3D. Okay, everything will be 3D. So meaning to say that right, you're going to have a y-axis, you're going to have a x-axis, you're also going to have a z-axis. So, which also means to say that, right, every point on the x, y, z axis can be at some distance away from the origin O. Okay, so position vector is really talk about the vector being at some distance from the origin O. So that's number one. And because of that, we can also move between point to point. So in displacement vector, we are traveling from point A to point B. Okay, so to find the displacement vector, you will need to take the position vector, which is measured from the origin. So, and of course, if I want to find from A to B, then I'll take the position vector of B minus away the position vector of A. Okay, so this one will be the displacement vector. One of the things that you need to remember how to do. And of course, last but not least, in JC, when we talk about vector, it's common that we use this thing called the unit vector. Okay, so the unit vector is by taking the vector itself divided by its own magnitude. So unit vector will always have a magnitude of 1. Okay, magnitude of 1. The usefulness is as per this yellow color box here. When do we use the unit vector? Okay, so you can find the unit vector, then you can use the unit vector to find a vector that is parallel to this. Let's say I want to know what is the vector that is parallel to my vector A. Okay, so I use my unit vector A prime, A hat. Then after which, right, if let's say you tell me that the vector I want is of a magnitude of 5, then what I will do is that, right, I will take 5 multiplied by the unit vector of A. And with that, I will be able to get a vector that is of a magnitude of 5 and at the same time in the direction of A. So this is how we can find the vector that is parallel to A, okay, by using its unit vector and then multiplied by the vector, that's the magnitude that we want. So this is how we can get a vector parallel to A and at the same time having the magnitude that you want. If you just use the vector OA itself, take note that vector OA, okay, which is over here, vector OA will have not only the direction, also of its own magnitude. Like for instance, maybe vector OA itself has a magnitude of 3. I cannot just take vector OA multiplied by 5. Then that will give me a magnitude of 15. I don't think that's what we want. Okay, so usefulness will be I can use the unit vector of anything at all. I multiply by the magnitude, then I will get a vector that is actually parallel to this vector OA and of the magnitude that you want. This is commonly what we do if we want to find this thing called the vector projection. For those who remember, so for vector projection, you take the length of the vector projection multiplied by the direction, the unit vector that you want to be parallel to. Okay, later we will take a look at that. Alright, so remember, key important point number 1 will be the unit vector can help you to find any vector parallel to this unit vector and of the direction as well as the magnitude that you want. Okay, with that, let's continue. Okay, next important point. the ratio theorem, which is we're going to use this ratio theorem to solve problem related to reflection of point. Okay, this is quite common. This is one of the common things that we do to use the ratio theorem. And of course, a ratio theorem is used in such a way that if you want to find a vector that cuts, okay, that cuts the line joined by 2 points, okay, in a certain ratio, then the ratio theorem will be able to help you. Take note that while in this example here, I use O as a start point, but it is not necessarily the case. So take note of what is your start point. And in this case, if the start point is O, so the OA is the one that the vector that gives you the point A, then OB is the vector that gives you the point B, and OC in this case is a vector that gives you the point C. So usually for A, the vector A and vector B, right, you will write the lowercase a, lowercase b, and even for C, right, we commonly will write the lowercase c. Yeah, so this is actually what will happen. And with that, if you want to find the vector OC, which cuts the line AB, so the thing that is being used to cut, you will write on the left side. Okay, the thing that is actually forming this line that you are trying to cut will be written on the right side. So take note that if let's say you are looking at vector OA, right, the corresponding number that you multiply to will be the other side. Okay, the other side. So we'll use Q. And of course, OB, okay, the vector OB, you use this length over here. Okay, the parts they're going to use will be on the other side. So it's not directly the number nearest you multiply to OA. It's not. So take note of that. So OC is QOA plus POB over P plus Q. Okay, take note that the question should tell you the exact ratio. So if I divide a line in the ratio of 2:3, okay, so possibly your P will be 2 and your 3 will be Q. Okay, so normally they will say that. But if I divide a line into the ratio, maybe not the ratio, to tell you the fraction of 2/3, then actually it kind of meant the same thing, which means to say that if I want to put AC, vector AC over vector CB, right, then it will be in the ratio of 2:3, or 2/3 is a fraction. So AC is 2/3. In this case, I can say that AC is 2/3 of CB. Then the ratio is actually also still 2:3. Then I'll write down the 2 and the 3. More importantly is that when you do vector, do remember to draw the diagram. Otherwise, you'll be quite lost. That is the main thing to remember. Okay, with that, let's move on to the next slide now. So apart from the thing that we mentioned, unit vector, ratio theorem, right, the next thing that will help us to solve a vector question is this thing called the scalar and vector product. And as the word implies, right, scalar product, after you multiply, you're going to get a scalar. So for the non-physics student, a scalar will just actually means to say you only have magnitude. Okay, this thing that you're going to get out of the product, you are not going to get it's not going to get a direction, right? It's just going to be magnitude. So in order to differentiate, right, we use the dot, okay, the dot to represent that this is a scalar product, or what we call a dot product, as named after the dot. So A dot B will be mod A mod B cosine theta. So mod A mod B, if you recall, right, these are the magnitude of A, and this one will be the magnitude of B correspondingly. Yeah. And theta is the angle between the two vectors. One point to take note will be the way you form this angle must be in such a way that two vectors are touching each other at the backside, and then you are directed. So the arrowhead must be at the end. Which also means to say that, right, if let's say you got a diagram like that, let's say this is A, then let's say this is B. If it's connected in this manner, then this angle here would not be the theta. Okay, a lot of people thought it's just the adjoining part. But basically, if you want to find this angle, the correct one should have been, if I extend the arrow of A to this direction, then the angle theta is actually here, right? So this is actually not the angle theta. Please take note of that. Yeah. Of course, apart from that, the product of it, which you will get from here, this is in fact just a, what we call a scalar. It is a magnitude with basically no direction. It's not really a vector. It's just a number. And of course, this is the geometrical form. If you talk about the actual product, which I suppose you should be pretty familiar already, which is like 1, 2, 3. If I were to dot with 2, 2, 2, then the dot product will be 1 times 2, right? This times this, right? Then plus 2 times 2, so 2 times 2, then plus 3 times 2. Okay, so after that you use a calculator, add them together, then this will be your dot product. Yeah, I hope you remember this. Okay, let's move on to the vector product now. So the vector product is actually the product of A cross B. The X here will represent cross, and the direction of where you cross, which one do first, is actually important. Unlike the case of dot product where it doesn't really matter, you can A dot B or B dot A, it will give you the same thing, but if you talk about cross product, it's not going to be the case. So when we talk about A cross B, which is from here to here, rightfully, we are going to get a vector that is in a direction. According to your right-hand grip rule, you have the grip bottom. So by right, your normal vector will appear here. Okay, this will be an N. In the diagram that I showed where the normal vector is up, actually this is B cross A. So it will be in this direction. This is a point to take note. The thing is that you could get an answer that is different from the answer key, but if you're going to do a cross product, you should expect that yours should be parallel to the answer key's answer, right? Just that it will be in the opposite direction. So there will be a difference in the sign, that's all. Number should actually be the same. So if you're doing a cross product, then you're supposed to get a vector that's perpendicular to both A and B. Like A and B. So, and of course, the geometrical form will be mod A mod B sine theta, and this N here really tells you the direction. Okay, the N hat here is meant to tell you the direction. And this part here, as I always check in my class, this is the magnitude. So which is the reason why if you look at my next expression, right, if I want to find the magnitude of A cross B, in fact, it will just be mod A mod B sine theta. Okay, mod A mod B sine theta. As for the how to do the vector product if it's an algebraic form, okay, I'll just briefly go through here, but I believe most of you should remember. I might not have enough time to go through this in detail, but let me show you this. So let's say 1, 2, 3 cross 3, 1, 0, right? So the way we do it is that, right, we always have to remember the covering method. The resultant will be a vector, right? So you want to find the first quantity at the top, so that I draw 3 lines first. The first quantity is that you cover away this part. Okay, you don't look at the 1 and 3. You do a crisscross here. So 2 times 0 minus, so 2 times 0 will be 0, right? 0 minus 3. Okay, it's always a subtraction. The only problem with the second one is you cover the second row, second row, then after that, right, you put a minus sign in front. That's what my teacher taught me in the past. So I put a minus, I always remember this. Then I put a bracket. Then you cover, it will be 1 times 0 minus 3 times 3. So this will be a negative 9. So a lot of times, because you forgot to put the minus sign outside, as a result of that, you could get a wrong answer. Okay, and of course, the last one, you just cover the last row, and then you crisscross again. A bit like the shoelace method for A method. Okay, so this is the vector and scalar product. Of course, this is meant as a recap to help you to remember, yes, these are the things that we have learned before, and they are being used in a question. So now if we continue, right, moving on to the next part, let's talk about application. So application wise, the first application will be whenever you think about angle, okay, angle, you want me to find angle between two lines or angle between a line and a plane, the same formula applies. We have to use the scalar product, the geometrical form to do so. Okay, so in this case, A dot B is equal to mod A mod B cos theta. So if I make cos theta the subject, and then this is the final formula. Yeah, and of course, most of the time when we talk about this A and B, the one thing that will change is usually the vector B or one of the vector, right? Because it could be the case where both A and B could be a known vector. You want to do an angle between that and also a line, or maybe between two lines, okay, or maybe between a line and a plane. So then what is your A and B is likely going to be changed. Usually at least one will be changed. Okay, for the case of, let's say, line with line, right, most of the time this A and B, I have to use the directional vector. So I call this D1 and this is D2. So let's say L is dot dot R, okay, L1 is equals to, let's say A plus lambda d1. Okay, lambda d1. So let's say these are all vectors. Then after that, right, we got L2. R is equals to, let's say this A1, this A2. Then this is lambda d2. Then after which, right, you have to take the directional vector, which represents the direction of the thing, to find the angle. Okay, so take note of also the case where you need to make sure that they are going away from each other when you find the angle itself. Okay, so this is an important thing to remember. And one of the very common thing, finding angle. And after you find angle, a lot of times you can also use the angle to do Picasso to find length as well. Is it actually possible? Even for the context of vector, it's possible. Okay, let's move on. So apart from that, let's talk about now between a line and a plane. So between a line and a plane, then you will have to use your normal vector. So okay, so this plane thing I will dwell into a little bit more in the next lesson. But for plane, one of the very useful formula that we're going to use is the scalar product form, which we talk about a normal vector. Okay, so you remember that. And you want to find the angle between the plane and the line. The thing that we do first is that we use the scalar product to find the angle between the line and the normal vector. So funny, right? Because this is actually not what we want. But however, we need to have a vector to be able to do the dot product. So I use a normal vector, which represents the plane, and also the vector A, in this case, which is a line. So if I were to dot them, I will still get the same scalar product formula. But because the angle that we have found is not the angle that we want, so you look at this, right? This entire thing is 90 degrees. Okay, this is 90 minus theta. So meaning to say the angle between the line and the plane will have to be this part. And because of that, we put it in, we will get this cosine 90 minus theta to become sine theta. So this sine theta is not a result of vector product. A lot of people thought this is because of vector product, that's why we got the sine theta, but no. This is still scalar product. Just that 90 minus theta, cos 90 minus theta will become sine theta because of the complementary rule thing. Okay, and of course, this is the formula for the angle between the line and the plane. Once again, most of the time, the A should be the directional vector of the line. Okay, please take note of that. Alright, let's look at the actual question now to see how this is being applied. A plane has an equation of r dot 1, 2, comma, minus 3 and equal to 5. The line L passes through point P with position vector 7, 4, minus 6 and is parallel to 7, 3, minus 5. Find the acute angle between the line and the plane. Okay, so the first thing we need to do is to write down the equation. Okay, that should be the first thing we will do. Write down the equation first. So for the equation of the plane, it will look like this. This is a scalar product form. So r dot 1, 2, minus 3 is equal to 5. Okay. Then for the line y, because it passed through P with position vector of 7, 4, minus 6 and parallel to 7, 3, minus 5. So straight away, this part, I'll use this as my directional vector. Okay, directional vector. And for the line, we were going to write this. So L dot dot R is equals to 7, 4, minus 6. This is a point which the line passed through, plus lambda of 7, 3, minus 5. Okay, so remember, the equation of the line is always a point plus lambda or mu of a direction. Okay, so these are the two equations. And from there, we are supposed to find the acute angle between the line L and the plane. If let's say at this point you are confused, my suggestion is why not we draw the diagram first. Yeah, so if I draw the diagram, okay, let's sketch it out here. This will have to be the plane. So the plane will have a line, okay, they have a normal vector. So this normal vector has a direction of 1, 2, minus 3. Okay, then after which, right, we're going to draw the line as well. So this is my line. And this line has a direction of 7, 3, minus 5. Okay, so this is r equals to 7, 4, minus 6 plus lambda 7, 3, minus 5. Okay, and now if let's say you're going to follow the formula that we seen just now, this is what's going to happen. Okay, so we're going to use the directional vector of the line together with the normal vector of the plane. And then we're going to use it to find our angle. So remember the formula is actually sine theta equals to, sine theta equals to the directional vector 7, 3 minus 5. And then we dot with 1, 2 minus 3. And then the entire thing, right, to find the magnitude of the vector, it will be square root 7 square plus 3 square plus negative 5 square. Then after which, square root of 1 square plus 2 square plus negative 3 square. Okay, then after which, you do a sine inverse to find the answer. So theta will be equal to the sine inverse of this. Okay, so this is how we do a question like that to find the angle. So the thing is that, right, you might need to be able to understand which one is the normal vector, okay, which one is the directional vector. If it's not clear to you from the equation, I would strongly suggest that you really write down like what I did. It is usually better, rather than you try to think about how to do it, which one is the vector to use. So that's the thing to remember. Okay, so now let's move on to the next part. Okay, application of scalar product. So now the second application is to help us to find this thing called the length of vector projection. Okay, so the length of vector projection is just to say that, right, imagine I put a light bulb at the top, and now if I were to put a light that shines downward, what happens is that this white color arrow that I see, right, will have a shadow that's cast on the bottom, on the ground, this part. So imagine this is a shadow. So what we're going to do is that we're going to find the length of this. And in order to find this, it has two things to do. Let's say you forgot what is the formula, right? There's two things to do. First of all, right, think of Dwakaso. So in Dwakaso, if I want to find this length, this is called the adjacent length, if you remember. This is adjacent, right? And in vector, although this is vector A, then this is a length of a magnitude A, the magnitude of A, magnitude of A. This is length A, right? So which also means to say that if I use Dwakaso, cosine will be equal to adjacent over hypo. A itself is a hypo. So if I look at this equation here, if I rearrange, my L will be mod A, mod A cos theta. Okay, so this is the first point. Okay, second point is that now we turn to look at our scalar product equation. So the scalar product equation is here. A dot B equals to mod A mod B cos theta. Then now, if I remove the mod B or let my mod B be equals to 1, okay, later I explain why, then I will actually arrive at this expression. And I want you to notice that the things on the right side is in fact the same as this. So meaning to say that isn't this going to be equal to this as well? Right? It makes sense, right? And this is the reason why when we want to find the length of vector projection of A onto B, right, the formula will be L equals to A dot B hat. So always remember the vector to project on is the unit vector. Okay, is the unit vector. And the reason why we need a unit vector, once again, you look at it, right? It is because I want to get this expression to be the same as this. So the only way is that the magnitude of B must be equal to 1. And when that happens, then we can reduce the equation to this. Yeah, okay, so this is the second recap. Okay, now let's continue. Right, so the second thing is to talk about how do we find, use scalar vector to find this thing called the foot of perpendicular. Okay, what exactly is foot of perpendicular? Let's say you have a point A here, okay, and there's a line L at the bottom. So if I were to draw a line from this point A to the line L perpendicularly, then I'm supposed to cut a point known as N. This N is known as the foot of perpendicular. Okay, so all these are the things that you're expected to know how to do before we can even do a question. Okay, this is the foot of perpendicular. And then from there, okay, to look at the N, right? Okay, from there, you can see that this N is also a point that is on the line itself. So which also means to say that, right, this point should actually satisfy the equation of the line. And just to give you one example, it just means to say this. Imagine your line L, right, has an equation of 1, 2, 2 plus lambda 3, 1, 2. And remembering that R in the equation of the line, R itself is in fact the any point on the line itself. So which also means to say that my coordinate or the vector ON, okay, which is a point on the line, right, must be given by 1 plus 3 lambda, 2 plus lambda, and 2 plus 2 lambda. Correct? Because it's a point on the line. So which means to say that this R value can also be used to represent N, which is a point on the line. And hence the direction, the position vector of N is given by the equation of the line. And this is quite useful because in the next step, let's say I want to find the foot of perpendicular N now, I need to find a value of lambda to give me this point. So how do we continue from here? Let's imagine your A is 1, 1, 1, just for the sake of simplicity. So now if I find the vector AN, then I'll get ON minus OA, which will give me 1 plus 3 lambda, 2 plus lambda, and 2 plus 2 lambda, minus away 1, 1, 1. And then from here, we will get an answer. Okay, I'm going to write here. It will be 3 lambda, 1 plus lambda, and 1 plus 2 lambda. Okay, so this will now represent the vector AN. And why do I do that? So now the last part, to find the value of lambda, important, we need to use the scalar product to help us. Because remember, any vector that is dot together, if the angle between them is 90, or what we call perpendicular, then the dot product will be 0. So now if I use AN, I dot this with the directional vector of C. Okay, just for the sake of demonstration, let's say my C is a vector of, yeah. So now if we do AN dot with the directional vector of C, let's say C is 1, 2, 3, then we will get 3 lambda, 1 plus lambda, 1 plus 2 lambda dot with 1, 2, 3, and then we will get, okay, let me write this again, 3 lambda plus 2 plus 2 lambda plus 3 plus 6 lambda, and then this will be equal to 0. Remember, the dot product must be equal to 0. So now if you were to solve for lambda, you will then be able to get the, okay, you then be able to get the lambda, which actually gives you this point N, right? So that's how you find the vector that is actually the foot of perpendicular. Okay, so this is how you find the foot of perpendicular. Okay, moving on to the next part. Let's look at an example of how to find the foot of perpendicular. So imagine you have the point A has a coordinate of 2, 3, 4, and the line L has an equation of 5, 6, 4 plus minus 2, 3, 1 t, where t is a real number. Find the foot of perpendicular from A to L. So now let's try to do this. Okay, imagine that we have a line L. Okay, this is called L, and then you have a point A over here. So what happens is that point A has a coordinate of 2, 3, 4, and then this is line L, which has an equation of 5, 6, 4 plus, okay, I put a t in front, t minus 2, 3, 1. So now if the question wants me to find the foot of perpendicular, which I draw a dotted line, and then we use n again. So this is actually A, this is n. And then once we find the foot of perpendicular of A to L. So how do we do this? Okay, remember, the first thing you need to do is that you can write down an expression of ON, which is the vector, the position vector of n. So ON should be equal to 5 minus 2t, 6 plus 3t, and 4 plus t, right? It is on the line, so it should have the same equation as the line itself. So this is ON. Okay, next we're going to find AN. So this is the second step. So AN is ON minus OA. So 5 minus 2t and 6 plus 3t, 4 plus t, we have to subtract away 2, 3, 4. And then with that, we will find the an to be equals to, let's see, 3 minus 2t, 3 plus 3t, and last but not least, just t, right? This is my an. Okay, last but not least, I want to find what is the t that will give me the n. So an, which is a vector perpendicular to my line L, you dot with the directional vector of the line L, which is minus 2, 3, 1. Okay, then it should be equal to 0. It should be equal to 0. So now if you plug it in, 3 minus 2t, 3 plus 3t, t, you dot with 2 minus 2, 3, 1, it should be equal to 0. Then after that, you do the dot product, find the value of t. Then after you find the value of t, you put it back into this equation here. And then you will be able to find the foot of perpendicular from A to L. Okay, so this is the equation to find the foot of perpendicular. This is how we do it. Okay, we have to make use of a few things. Number one, the line which the foot of perpendicular lies is going to be the equation we're going to use to represent the position vector of n. Okay, number two, I need to form a line from A to n, okay, to get that line, and then we do a dot product with the line L, and with that we will be able to find a value of lambda that will be able to give us the position vector of n. Because the meaning of the equation of the line is just that every point on the line itself is represented by the equation with a specific value of t. So the main point is to find out what exactly is this specific value. Okay. Now, coming to the last part, vector product. So for vector product, as mentioned just now, we have A cross B, mod A mod B sine theta n hat. And the n hat, as I mentioned just now, this is really to give you the direction of this vector. So if I want to use the magnitude only, a lot of times, a lot of questions we're going to do, right? The application is really to use the magnitude only. So I remove the n hat, and then as a result of that, right, I will have mod A mod B sine theta. And you multiply a half to it, okay, multiply half to it, then that gives us our first application, which is to find the area of a triangle. So in the area of the triangle, the A and B, mod A mod B, is the two known length of the triangle, and then the angle that is sandwiched in between. So remember, half AB sine C, so the angle is in between. Then with that, we can just use the vector product to help us to find that. Since half mod A times mod B, half mod A times B, okay, A cross B will give us this expression, right, which is the same as our half AB sine C. So if we equate the two of them, then the area of a triangle is just half times half A cross B, and then the modulus of it. So that's how we use vector product to find the area. An extension to this will be if you're talking about the area of a parallelogram or a rhombus, then I will remove the half. Because for parallelogram, it is basically you have two triangles that is entirely the same. Okay, if you find the area of one triangle and multiply by 2, I will get the total area of this parallelogram or rhombus. Okay, so this is a point to note. I can also use this formula to find the area of parallelogram or rhombus. Okay, next one. We can also use this to find the shortest distance from a point. Let's say the point A is here, okay, to a line. So how do we do it? Is also making use of Dwa Castle. So imagine that you have once again the vector product, and I just want to use the magnitude part. So A cross B is mod A mod B sine theta. After which, right, if I divide by the mod B over to the other side, then over here I will just get A cross B hat, okay, the magnitude of it, then equals to mod A sine theta. Now if I turn our attention to the Dwa Castle now, imagine this is a right angle triangle. Sine theta would have been this length S divided by this length A. Okay, so S over mod A. So now if I move the mod A to the other side, I'm going to get S to be equal to mod A sine theta. Now if you look at this expression, and this expression, they are the same thing, right? So which means to say this is equal to this. And this is how it arrived at the equation. Shorter distance S between a point and a line L. Okay, so this is how we arrive at the equation. While I would say you do not need to memorize the way to derive, but it is useful to know, because if you want to just memorize the formula for calculation, you could, but there are times where you memorize wrongly, and there's a lot of things to memorize already. And second possibility is that you might actually forgot what were the condition when the equation came about. So my suggestion is always to try to work it out yourself. But if you really find that you even don't have time to do that, then really make sure you understand the equation first before you go for the exam. Don't just memorize it. Okay, this will be our last question for today. The coordinate P has a coordinate of 2, 7, minus 1. Line L has an equation of 1 plus 4 lambda I plus 3 lambda J plus 2K. Find the position vector of foot of perpendicular from P to L. Okay, once again, as mentioned, let's draw out the diagram. So the diagram will look like this. This is my line L. Okay, this is my point P. Okay, then after which, right, point P has a coordinate of 2, 7, minus 1. I always like to write in the column vector form. Then on the line equation, right, okay, if you find this confusing, we can do this. So R is really just ijk, right? So we arrange like that. 1 plus 4 lambda, 3 lambda, and then k is 2, right? So 2, right? So this is how we arrange it. If you separate out, you get 1, 0, 2 plus, okay, plus 4, 3, 0, and then you put a lambda. Okay, because for the last one, the z, there isn't any lambda. So it will just be 4, 3, 0. Okay, z has no lambda. And for the first one, there is no, the point, right, the 1, 0, 2, for the y, there isn't any number that's added to the 3 lambda. Okay, so this is the equation of the line. And then after which, right, we need to find the position vector of foot perpendicular. Basically, the process will be repeated again. So we draw a dotted line here. And then after that we have to determine n. So I think I just run through the steps, which is, right, you need to find your ON. Okay, so ON is given by, once again, 1 plus 4 lambda, 3 lambda, and 2, right? That's your ON. Then after that, you find your PN, right? Because PN is a vector that's perpendicular to the line. So PN would have been ON, 1 plus 4 lambda, 3 lambda, 2, minus away, 2, 2, 7, minus 1. Okay, so then after that, you do the computation. So once you find a Pn, then you do the dot product with the directional vector of L. So last but not least, this is number 1, right? Number 2, the third point will be do the dot product between, okay, between Pn dot with the directional vector of the line, which is 4, 3, 0, right? And then it will be equal to 0. Then you solve for your lambda to find your ON. Okay, then for B, right, the shorter distance from P to L, okay, you can use the formula that we saw just now, but even that, over here, I'm going to show you an alternative method to do this. So since we already find N already, right, so actually, if you want to find the shorter distance between P to L, the reason why the question have given you A first is because that they wanted you to continue from here. So once you find your ON, you will know your PN as well. So I can take PN, the modulus of that, okay, modulus of PN. Once you find that, then that will be the shortest distance from P to L. Yeah, actually PN is the shortest distance from P to L already. So this is how a question can actually make a turn from initially, oh, I remember I need to use a formula, to actually, if you follow the direction of the question, you follow their guiding, you find the point of foot perpendicular, you can then use that to find the shorter distance from P to L. So the purpose of showing you this is that while you can use the you can use the formula to calculate the shorter distance, you can also use the full perpendicular to help you to find the shorter distance. Okay, so this will be the last question for this video. In the second part, I will focus a lot more on the application of lines and plane. So this is to just lay down the ground rule or the foundation for you to continue in the next video. So at any one point in time, let's say there's any part of the video that you are not sure, feel free to make comment, and then after that, I will try to get back to you, or can actually drop us an email. Okay, you can go to our website, email us, or leave a comment on the website as well. So these are the ways that you can engage us. Or maybe just message me, no problem. Okay, if you like the video, please help to subscribe and share with the rest of your friends.